Hi guys, welcome to Maths with me, Mr. SE, your teacher for today. So today we're gonna discuss about interactions and forces. This video begins our study of mechanics, the branch of physics that consider how interaction between objects affect the motion of those objects. Just as human life would be dull without social interactions, the physical universe would be dull without physical interactions. Social interactions with friends and families change our behavior. Physical interaction change the behavior, motion, temperature, etc. of matter. An interaction between two objects can be described and measured in terms of two forces, one exerted on each of the two interacting objects. A force is a push or pull. When you play soccer, your foot exerts a force on the ball while the two are in contact, thereby changing the speed and direction of the ball's motion. At the same time, the ball exerts a force on your foot, the effect of which you can feel. To understand the motion of an object, whether it be a soccer ball or the International Space Station, we need to analyze the forces acting on the object. To correctly identify forces, you should be able to describe them as type of force exerted on object by object. For example, contact force exerted on the ball by the foot, gravitational force exerted on the space station by Earth. Forces exerted on macroscopic objects, objects that are large enough for us to observe without instrumentation, can be either long-range forces or contact forces. Long-range forces do not require the two objects to be touching. These forces can exist even if the two objects are far apart, and even if there are other objects between the two. For example, gravity is the long-range force. A gravitational force exerted on Earth by the Sun keeps the Earth in orbit around the Sun, despite the great distance between them, and despite the other planets that occasionally come between them. The Earth also exerts a long-range gravitational force on objects on or near its surface. We call the size of the gravitational force, also called the strength or magnitude of the force, that a planet or moon exerts on a nearby object, the object's weight. Part 3 of this video treats electromagnetic force in detail. Until then, you can safely assume that gravity is the only significant long-range interaction unless the statement of a problem indicates otherwise. All forces exerted on macroscopic objects, other than long-range gravitational and electromagnetic forces, involve contact. Contact forces exist only as long as the objects are touching one another. Your foot has no noticeable effect on a soccer ball's motion until the two come into contact, and the force lasts only as long as they are in contact. Once the ball moves away from your foot has no further influence over the ball's motion. The idea of contact is useful simplification for macroscopic objects. What we call a single contact force is really the net effect of enormous number of electromagnetic forces between atoms on the surface of two objects. On an atomic scale, the idea of contact breaks down. There is no way to define contact between two atoms. In other words, there is no unique distance between the atoms at which the force they exert on one another suddenly becomes zero. If the concept of force is to be useful in physics, there must be a way to measure forces. Consider a simple spring scale. The scale span is pulled down. A spring is stretched. The harder you pull, the more spring stretches. As the spring stretches, an attached pointer moves. Then all we have to do is to measure the applied force, is to calibrate the scale so the amount of the stretch measures the magnitude of the force. For many springs, the extension is approximately proportional to the force, which makes calibration easy. In the United States, supermarket scales are generally calibrated to measure forces in pounds. In the SI system, the unit of force is the Newton. To convert pounds to newtons, use the approximate conversion factors. There are more sophisticated means for measuring forces than a supermarket scale. Even so, many operate on the same principle as the supermarket scale. A force is measured by the deformation, change of size or shape it produces in some object. The magnitude of the force is not a complete description of the force. The direction of the force is equally important. The direction of the brief contact force exerted by a soccer player's foot on the ball can make the difference between scoring or a goal or not. Force is a vector quantity that must be added or subtracted using the same methods used for other vector quantities such as position, velocity, and acceleration. When more than one force acts on an object, the subsequent motion of the object is determined by the net force acting on the object. The net force is the vector sum of all the forces acting on an object. An essential tool used to find the net force acting on an object is a free body diagram, a simplified sketch of a single object with force vectors drawn to represent every force acting on an object. The net force must not include any forces that act on other objects. To draw an FBD, number 1. Draw the object in simplified way. You don't have to be Michelangelo to solve physics problem. Almost any object can be represented as a box or a circle or even a dot. Identify all the forces that are exerted on the object. Take care not to omit any forces that are exerted on the object. Consider that everything touching the object may exert one or more contact forces. Then identify long-range forces. For now, just gravity, unless electric or magnetic forces are specified in the problem. Number 3. Check your list of forces to make sure that each force is exerted on the object of interest by some other object. Make sure you have not included any forces that are exerted on other objects. Number 4. Draw vector arrows representing all the forces acting on the object. We usually draw the vectors as arrows that start on the object and point away from it. Draw the arrows so they correctly illustrate the direction of the forces. If you have enough information to do so, draw the lengths of the arrows so they are proportional to the magnitudes of the forces.